Okay, so let's go through some intuition behind the denoising diffusion process. So the first question we might ask is why use diffusion at all? And effectively, this is a solution to a well-known problem of sampling from an observed distribution. So we can imagine we have a set of samples, and these could be images, and we want to generate more samples that resemble the samples in the data set. And so far, there have been several common solutions to that, including variational autoencoders, normalizing flows, and GANs. But all of these solutions, and the ones not listed here, have certain disadvantages. So first of all, diffusion models are quite simple, quite easy to train, and they also seem to deliver state-of-the-art quality. So that's the main reason why we might want to use diffusion models in 2023. Okay, they are, however, quite expensive in terms of training and inference. So there's a certain cost to be paid, but because of the quality that they provide and the fact that they're quite easy to train, might be enough to consider these as good candidates for generative models. So we'll start with some visual intuition for what diffusion denoising process is based on. So we can start with a set of images that, to us, probably look quite likely at a first glance. They look like images that could have been photographed somewhere at some point. And that basically is a manifestation of us having learned the distribution of natural images. So we have some knowledge of what a real image should look like, and these samples seem to have those features. These samples are actually not real; they are generated by Stable Diffusion, but still, that's a model that has been trained successfully, and it is able to generate some convincing samples. Now, the question is, what happens when we start adding a small amount of Gaussian noise? We can immediately see that there's some noise, some distortion present in these images, but we can still retrieve most of the information, and we can still tell it's probably close to these samples look quite likely, and it's a good approximation of what a real sample could look like. Now, if we keep taking more and more steps, this distortion will get more prominent, and a lot of information present in the clean samples will actually start to disappear from our images. And eventually, we will drift away from our data manifold, and the samples will no longer look like anything specific. So we can imagine a function that assigns a value of likelihood to any image that we see. So X would be an image, and Q of X would give us a value that's quite high for the clean samples, for the samples that we've seen in the first instance, and much lower for the samples with severe noise. And we can imagine this in two-dimensional space, the distribution of this function with high values assigned to samples with high likelihood and low values for samples lying outside of our domain. Okay, so that can be described by a Q of X distribution. And then what we've done is we've actually progress through a diffusion chain by adding more and more noise, and that can be modeled by conditional distribution. So we condition a given image on the previous step. So if we have a little bit of noise added to our image, the next step will also have that level of noise plus maybe a little bit more noise. Okay, so this is just how we formulate the forward process of diffusion. And what we've done in the example in the previous slides is we've started in a location where this likelihood was fairly high. we started just adding pure Gaussian noise, nothing fancy, and we started drifting away from our data manifold. Okay, so that's basically the forward process of diffusion. At this point, we can also make a hint related to the diffusion schedule, because the magnitude of these steps, the variance of the added Gaussian noise, is really for up to us to decide. So we always start with the clean data distribution, the beginning of a chain. We have a temporal index t equals 0. But then large T defines the number of steps we take as part of our forward process. And within each step, we can also exactly tune each specific variance of the added noise. So at each step, we might take whatever we find suitable. Okay, so there are obviously some defaults that are commonly used, but it's in the hands of the designer to decide the actual diffusion schedule. And that's what schedule refers to whenever you see schedule being mentioned in the context of denoising diffusion models. Okay, so again, this is how we've gone through these are two, we can imagine these two dots as ends of our diffusion chain, and everything in between, the magnitude of these steps is basically determined by the schedule. Okay, so in the second part of this episode, we'll go through the key equations of DDPM, which stands for Denoising Diffusion Probabilistic Models. It's basically the vanilla implementation of denoising diffusion. There have been some developments, some alternatives proposed since then. However, when we talk about diffusion, we often talk about DDPM. Okay, so that will be a good start for understanding diffusion models. This is where it all started. And we go through the equations without really deriving anything, focusing more on what these equations stand for and how to understand the whole framework, okay? So the forward process is what we've done so far. We've gone through from clean images to noisy images. And whenever we take a single step of the forward process, we add a little bit of Gaussian noise. And that's so the distribution, this conditional distribution that has been mentioned before, is essentially a Gaussian distribution, because the mean will depend on our previous sample. It will be scaled by a certain factor, and then there will be some Gaussian noise added to that sample. So that's quite easy to define, quite easy to compute as well. And then if we take multiple steps, you can actually find a simplified equation for going from x0 to any xt without going through a chain of xt, t minus 1 to any given t. We can actually jump directly, because that distribution is also Gaussian if we define a forward process as Gaussian. And again, the derivations are available in the papers and also in the notes that are part of this course. But the equation remains quite similar. So it's a scaling of the original x0 as opposed to xt minus 1, and some pure noise with zero mean added to that sample. Okay, so that's the forward process. That's very easy to compute, very easy to define, but that's not really interesting if we don't define a reverse process, because it's the reverse process when we go from a pure Gaussian to a real sample that allows us to actually generate new stuff. Okay, so reverse process aims to reverse that chain. Now that's much harder to do unless we realize that if the steps are small enough, if these additions of noise are gentle enough, the reverse process at each step can also be modeled by a Gaussian. So if we have this information, we can define the opposite conditional as a Gaussian distribution. Now, the tricky part is to find the parameters of the distribution, and these parameters will depend on the given sample xt. Okay, so to get the previous step in the diffusion, what could have been the cleaner sample, the previous step, we actually need to approximate these parameters based on the current step. So commonly neural networks are used for that because they act as a very useful tool for parameterizing these distributions. These are generally quite complex functions to approximate, and neural networks do a pretty good job at that. Another thing is that in the early works, sigma theta is often fixed as a constant. Without going into the detail, we can actually get a pretty good idea of the variance at each step. However, there were also some follow-up works that indicated that predicting the sigma theta is actually quite beneficial. But we won't be doing that in this particular example, just for the sake of simplicity. We'll focus on the most basic implementation with prediction of the mean parameter. Okay, so this is where we are, and we are most interested in approximating the mean based on parameters theta of the neural network. Okay, so again, if we go through the formulations, we will find out that this mean can actually be approximated as a linear interpolation between xt and x0. And so x0 is what we can actually predict instead, which will make some things easier. The linear scaling between these two samples, again, can be derived through a set of operations that are available in the paper, but we won't go through that. So all the constants that are easily to compute beforehand are in gray color here, and what we have to focus on is what happens with the rest of the equation, which is the linear interpolation between x0 approximation and xt. So that means that we have access to xt, so we can actually reparameterize this problem and focus on approximating x0. If we approximate x0, we can use this equation to approximate the mean parameter. Okay, now how do we find x0? So x0 will actually be xt minus the noise that has been added to the sample. Noise indicated by the epsilon. And again, we need to use some scalings because the noise epsilon here comes from a normal distribution with zero mean and unit variance. And obviously, depending on the temporal index t, this noise will be added with different magnitudes. But we can, again, derive that directly from our schedule. So at this point, we can get x0 and again, we have access to xt by predicting the exact shape of noise. So if we follow these equations, this is the equation that we just looked at, where we use noise subtraction. We can get an approximation of the mean parameter, and then we can substitute that. We can effectively substitute the first equation here, x0 to x0 in the second equation. And after some simplification of the constant parameters, we get this last equation. It looks maybe a bit similar to the first equation, but it is different. And again, the first equation is an approximation of the clean sample, and the last equation is an approximation of the previous sample in the chain. So not the clean sample, the previous sample in the chain, just so we can progress through the reverse direction of the diffusion process. Okay, so that's the most important equation for DDPM, because at this point we can realize that all we need to do with our neural network is predict the shape of this epsilon noise. Okay, so if we find a network, if we find a model, if we train a model or find a model that can approximate this shape epsilon quite well, we can actually perform a reverse process by using this equation. Okay, so now the last part of this episode is just going through the equations present in the DDPM paper. The actual algorithms for training and sampling. And yeah, just to summarize, the reverse process where you go to the previous sample based on a current sample t is basically a normal Gaussian distribution where we use the mean, where we approximate the mean using the neural network in this equation, and sigma t is also predetermined. So once we have all these components, we can actually progress through the chain multiple times by following this equation and updating our t and xt. Okay, and now for training, and we will basically take the this algorithm directly from the DPM paper. What we do for training is we go through a loop over all of the samples in our data set. And these samples are represented by x0. We're taking clean samples from the distribution of the observed data. Okay, and at each point we will want to sample t, the stage of our diffusion, uniformly. So it could be it's just as likely to sample something near the end of the diffusion where our sample is basically a pure Gaussian, or something near the very beginning of diffusion where we are very close to a clean sample and there's very little denoising to be done. And then at each step of our training loop, we want to sample epsilon. And epsilon comes from a normal Gaussian distribution with zero mean and unit variance, okay? So it's always the same type of distribution that epsilon comes from, the same normal distribution. And that's basically what the network is supposed to predict. Now, depending on the value of t that controls the stage of diffusion, we will add this epsilon at a specific magnitude to that temporal index. Okay, so at each step of a training loop, we will be taking gradient descent, as can be expected with neural networks. The first thing we do is we add this epsilon noise to our clean sample x0. Okay, and as discussed earlier, this is basically a linear interpolation in pixel space in this case, using these two specific values for scaling. And again, these values can be derived from in the paper, are derived in the papers and derived in some of our notes. Okay, but the first important step is that we're essentially following a forward process here during training. We are adding some epsilon noise to our sample based on temporal index t. Okay, so we feed that into the network, and obviously the temporal index t as well. As we've discussed earlier, the network will take the temporal index to have a little better understanding of where we are in the within the diffusion process. Okay, so this network should produce an approximation of this epsilon, right? And we want this approximation to be as precise as possible. So we basically compute some type of error between these two. And this error could be something like L2 norm, but we can also use other types of distance metrics. But essentially, we want to bring this epsilon ground truth and this epsilon network output close together. And to do that, we've tuned the parameters theta of our neural network. And that's all there is to it. So this long equation in line 5, what it really says is make the network produce the exact shape of noise that has been added to the sample, right? Governed by this forward process definition that we have here. Okay, so that's that for the training, and the next bit is sampling. So once we have trained a network that can hopefully predict this epsilon shape quite reliably, we can perform sampling. And sampling will involve proceeding through the entire step, the entire chain of diffusion. So what we will do is we first sample our first approximation, so to speak. So the approximation of something at the very end of the diffusion can basically be sampled from a pure normal distribution again, because we're at the very end of the diffusion. So all information is effectively lost. So that's our starting sample, as just a sample from a Gaussian distribution. And then we go in a loop through all the steps of diffusion. So during training, at each time we were just focusing on a single step of diffusion, uniformly sampled from potential values of t. But here we go from the big T to the very end of diffusion, approximating our clean sample by following the reverse process. Okay. So at each point, we will add. First of all, we will want to sample from again a normal Gaussian distribution. This will be basically for the stochastic component of our reverse equation. Okay. But Z will also be 0 at the very last stage of diffusion, because at the very end, when we have a clean sample, we actually don't want to add any noise. and the variance is very low. So we basically just extract the mean. But other than that, there will be this stochastic component that basically makes our distribution of the reverse process Gaussian, right? The Gaussian distribution will have this stochastic component. So once we have done that, we sample the noise present in the XT. We propagate through our network to approximate the noise present in T, and it's a different type of noise than the Z in the previous line. So it's a bit confusing, maybe how it's defined in the paper, but this Z theta is basically our epsilon theta, basically what the network predicts as the noise epsilon inside the sample XT at the stage T. And at the very beginning, this will obviously be that X large T will be the input here. Okay, so what's the noise that the network predicts to be present in this sample or any sample at a specific stage. Okay, and obviously, as one of the as shown in one of the previous equations, we will want to remove that noise from our current sample. And we do that by following the reverse process. This comes from the reverse process equations. Again, this featured in one of the earlier slides. So basically, this should give us the mean of our distribution, the mean of the previous step. Not the clean sample here, but the mean of the previous step. So if we are at T equals large T, this will give us the mean of the step T minus 1, large T minus 1. Okay, so what could have been the mean of the previous stage, right? And then once we have the mean of our Gaussian distribution, we can add the stochastic factor. This is what the Z was for. It's for adding this variance. So basically, we don't have zero variance. We're actually predicting a Gaussian distribution at each time. And sigma T is, again, one of the parameters of our reverse process that is not learned in the basic version of DDPM. And basically, we assign this because this effectively is a sample from the Gaussian distribution with this mean and this variance. And we assign that as the next value of our XT. Okay, and then we use that as our XT for the next step, and we go over and over until we reach the end of the loop. And that's about it. At the very end, we just return X0. Okay. By progressing through this entire chain, we eventually get to the index T of 0, and that's our approximation of our clean sample. So I think that's about it for this episode. What I also want to show you is a notebook that's designed to illustrate some of these equations in the forward and reverse process. So I'll go on and do that as well. Okay, so that's the main page of the course. If you scroll down, you will eventually find the list of all the available notebooks. And to illustrate some of the ideas in this episode, we can use this first notebook called Diffusion Sandbox. What this allows us to do is illustrate some of the equations that we have for the forward and reverse process, and also illustrate the images that will be produced from specific distributions. So it takes a while to import all the necessary packages and libraries. Okay, so in this notebook, we will start with a sample image. It's one of the images generated by Stable Diffusion. And what we will do is just illustrate some of the key steps. So in general, when we perform diffusion, we want our images to be within -1 and +1 range. So if they're between 0 and 1, as they usually are, we need to transform them when we want to perform diffusion with them, and then transform back when we want to display them. So I've created some functions for that. We have some functions that define our diffusion schedule. And then we also have the forward process, okay? So we have specific functions that will allow us to do forward step or forward jump. In this case, forward jump allows us to get a sample at T based on a sample X0, the clean sample. So that allows us to get any T in a single step from 0, okay? So if we do that, we can actually display some of these samples using these the equations above. So in this case, we have various stages of diffusion. And the first row also shows you the mean of a Gaussian distribution at a given stage. Okay, so that means that the mean is generally a scaled down version of the input. So you can see at 0 it's basically the input, but then it converges to 0 in a linear fashion, right? The magnitude of that component is decaying as we go further down the diffusion process, and the remaining columns. So yes, I think I said row. So in the first column we have the mean, and in the remaining columns we have samples from each distribution. So you can see that there's this stochastic component added at each time to the mean component, and that's how we sample from these Gaussian processes. Okay. The next example features the forward jump. So in the previous example, we have used forward jump to go directly to a specific value of t. But here we can show that we can also use a forward step to go one step down the line based on any given sample, right? So if we consider step-to-step transitions, we can also use the forward step method. Okay, and then there's the reverse process, and here we have a more detailed descriptions of the equations and how they exactly work, and we can also visualize how the reverse process is performed, assuming we have a good approximation of the epsilon shape. Okay, so there's quite a lot of detail in this notebook, so I won't be going through all of it, but hopefully that can allow you to understand the details of the forward and reverse process a little better. So I hope you check that out later on. And in the meantime, I can recommend you follow to the next episode where we have where we go through the details of diffusion applied to images specifically.